We investigate optimal control of a series elastic actuator through a throw and catch task. A series elastic actuator consists of a linear or rotary motor configured with a spring between its output and the load. They are frequently employed in applications with unpredictable contact with the environment, such as legged locomotion and human-robot interaction. Series elasticity is particularly suitable for these tasks. However, the challenges introduced by reduced stiffness must be accounted for by an effective controller.
The goal of our project was to model, simulate, and control a 1-degree freedom SEA robot that repeatedly bounces a ball to a set reference height with minimum energy consumption. Assuming perfect kinetic energy recovery by the motor, the energy spent is equal to the energy dissipated by damping. The system dynamics can be described as bimodal linear, where two different linear dynamical models describe when the ball is in contact with or not in contact with the robot arm. The contact is modeled as an inelastic collision with a massless end effector, where the kinetic energy of the ball is transmitted to the motor arm assembly via the arm stiffness. Finally, we assume there is zero mean Gaussian noise on our motor control signal.
We use direct methods to compute trajectories for the motor, arm, ball system to repeatedly return the ball to a reference height. The trajectory is divided into a descent, capture, and ascent phase. Discrete time steps and a piecewise formulation of the discontinuous mechanics allow for a convex energy minimization problem. A second outer loop performs a non-convex optimization over the time step durations, enabling a flexible length of each phase. Shown here is an example trajectory outputted by the direct solver. Energy cost was most influenced by the upwards reach limit of the arm and the maximum time allowed for the task. Suboptimal convergence of the non-convex solver was common, thus requiring a high-resolution grid search over the time increment durations.
To track the pre-computed optimal trajectory, we implemented LQG control. The control is computed based on a finite one-bounce horizon, and since our desired motion is periodic, we can apply these same gains infinitely in time. Thanks to separation principle, we can use a state estimate from an EKF that takes in noisy measurements from a motor and arm position encoder and an arm load cell to compute an innovation based on a bimodal linear sensor model. Here's the full system in action, tracking the optimal trajectory in action on the right and depicted on the plots as dotted lines. We observe that the trajectories are relatively well tracked. However, we've noticed that the bounce height error and extra energy consumption suffer greatly by using the EKF state estimate rather than ground truth to compute the trajectory tracking feedback control. However, we're quite satisfied with the performance. Thank you.